Among several reasons which give both importance and I think also ultimate certainty to the advancement of spaceflight, probably the most fundamental is simply the compelling urge of people to want to explore and to discover. The surface of the Earth now is, of course, largely explored. And as we know, rockets and satellites have already begun to explore conditions just outside the Earth's atmosphere. So it's really not surprising that currently a lot of serious scientific thought is being given to some of the problems of exploring other planets besides the Earth. Now, we're going to be concerned here almost entirely with technical matters, aerodynamic heating, deceleration, and the like. But before we get into those, I'd like to spend just a moment on a point of history. We know that for thousands of years, people have been studying the planets. The Babylonians, for example, made surprisingly complete studies of very accurate calculations of all 5 of the planets that are visible to the naked eye. They recorded their studies on clay tablets in cuneiform. We have several examples here which can show. These 2 tablets here are just 2 of a large number of similar tablets that describe the results of their studies on the planet Mars, a planet which 3,000 years later is still very much the center of a lot of study. The Babylonians weren't the only peoples of antiquity that studied the planets carefully. The Egyptians, the Greeks, and the ancient Maya also studied them closely. And all of these peoples realized that there was something special about the planets because they moved in a different way throughout the skies than all the other stars. But they didn't realize just how special, because it's only been the last 300 to 350 years, roughly since the development of the telescope, that it's been realized that the planets are all just brothers and sisters of the Earth. And with this realization, the interest of a lot of scientists, of philosophers, and many laymen was immediately excited to a rather high pitch, at which level I think it still remains about some of the basic questions as to what it's really like on these other planets, or if there's any form of intelligent activity on these other worlds. Well, we believe that before too long, some instrumented vehicles will first be sent into the atmospheres of the planets and give some partial answers to these basic questions. And later, much more complete answers will be obtained by sending a manned vehicle into the atmospheres. Well, one of the first questions then that we want to consider is which of the planets have atmospheres, because not all of them do. Mercury, the planet closest to the Sun, doesn't have any significant atmosphere. But we know Venus has an atmosphere because of, say, pictures like this. This is a greatly enlarged picture of the planet Venus, where we've superimposed a dotted line along a diameter. Now you notice that the tips of the horns of the crescent Venus here extend well beyond a semicircle, so that what you're seeing here is just the twilight in the atmosphere of Venus. The Moon never shows this sort of behavior. You see that the horns of the crescent Moon never extend even to a semicircle, because the Moon doesn't have any atmosphere. Now, Mars never appears in a crescent phase like this. It's never backlighted, and it's always lighted from the front because it's in a more distant orbit. But we can use a different photographic technique there, one that's a lot more interesting from a scientific viewpoint. This is a composite of two photographs in different types of light. The left portion has been taken in infrared light, and this penetrates the haze of the atmosphere, so that what we see here are just surface features on the solid globe of the planet Mars. But now over here, in the ultraviolet portion of the photograph, this type of light doesn't penetrate the haze of the atmosphere. So what we see here is just a picture of the atmosphere, the external shell of gas that's around the planet. The difference is an indication of how thick the atmosphere is, because the picture on the right is a little bit larger. This is about 100 miles for the planet Mars and indicates a very sizable atmosphere. On making calculations of the aerodynamic heating and the deceleration, we're going to be using several quantities, which we can introduce here. Let's say that this is a planet's surface, and we have a vehicle in a circular orbit. This is the simplest type of orbit. And let's say the velocity here is u sub c. We use a subscript c to denote the circular orbit. Now, if this is the center of the planet, and this is the radius, the gravitational attraction is exerted towards the center, so we'll represent that by the gravitational acceleration g. And we have radially outward here the centrifugal acceleration, which is the square of the velocity over the radius. So that now, if these are in balance for the equilibrium case of a circular orbit, we have then that the gravitational constant just balances the radial acceleration term. So that the velocity which we're going to be interested in here, u sub c, from this is just the square root of g times r. Now, we're going to be interested in this because of its importance to heat transfer, but we're also going to be interested in the gravitational constant because of its importance to deceleration. So let's take a look over here at some models of planets, 4 of them: Venus, Earth, Mars, and Jupiter, which we'll be considering more later. Let's take a look at the Earth first because we're most familiar with it. The circular velocity for the Earth is 26,000 feet per second, and the gravitational constant is the familiar 32 feet per second per second. We compare that with Venus here, which we see is about the same size as the Earth. The circular velocity is just a little less than for the Earth. The gravitational constant is also just a little less. So we'd expect just a little less aerodynamic heating and a little less of a deceleration problem for Venus than for the Earth. Now, Mars is much smaller, as you can see. It's only about half the size of either Venus or the Earth. And correspondingly, the circular velocity is 12,000 feet per second, only about half. The gravitational constant is likewise less than half. So we expect a lot less severe aerodynamic heating problem, as well as a less severe deceleration problem for Mars. Now, Jupiter presents a greatly different picture. We've shown here just a drawing of a portion of Jupiter, because to this scale, Jupiter would be a sphere that is about 11 feet in diameter. Because it's so large, the circular velocity is 140,000 feet per second. And this would result in a very severe aerodynamic heating problem. The gravitational constant, 2.6 times the Earth's value, would also mean that we would expect a lot more severe deceleration problem on Jupiter than on the Earth. Now, as far as the gases in the atmospheres are concerned, in the Jovian atmosphere, we believe that there's a large amount of hydrogen, probably also helium. It's known to have quite a bit of methane and a certain amount of ammonia. These are not very pleasant gases, of course. Mars is better in this respect. It's believed to have a lot of nitrogen and only a lesser amount, or moderate amount anyhow, of carbon dioxide. The Earth, of course, we know, has nitrogen and oxygen in its atmosphere. Venus, it's known to have quite a bit of carbon dioxide, and it's believed to have a lot of nitrogen, but the big question mark on Venus is the oxygen. Don't know how much oxygen is there. And there's an interesting thing about Venus. If we compare the planet Venus to the Greek goddess of love, the famous Venus de Milo, which is a statue now in the Paris Louvre, we have to conclude that the planet Venus may be misnamed, because in contrast, this Venus, very coyly and very bashfully, always keeps herself perpetually draped in a thin mantle of white clouds, so that no one has ever seen the physical surface or the physical features of Venus. Now, in making calculations of the aerodynamic heating and the deceleration, a question often arises, and it's this. If we don't know for sure exactly what gases are in these atmospheres, how can we make calculations which we really have confidence in? And I'd like to take a moment to explain that. Let's suppose that we have a vehicle that's coming into the atmosphere here, and we compute the deceleration all along the trajectory, then find its maximum value. Well, the maximum value of the deceleration turns out to be proportional to the gravitational constant first. Then it involves a function of the lift-drag ratio of the vehicle and the square root of the radius of the planet. But then a parameter beta occurs, which depends on the atmospheric characteristics. And this is the only place where the characteristics of the atmosphere enter. Beta is the rate of change of density of the atmosphere with respect to the altitude y, where y would be the altitude measured with respect to the surface of the planet. It's minus because as we go up in altitude, the density decreases, and we have a row here. So that if somehow we can measure the rate of change of density with altitude, we can determine beta. And this can be done as follows. Suppose we have a star out here that passes behind the planet, a star occultation by the planet. And we measure the light intensity of this star as a function of the distance d from the planet. We make a little graph here of the intensity of the starlight as a function of d. Now, as the star comes to the atmosphere and approaches the atmosphere, the intensity of illumination does not change until we really hit the atmosphere, and then it doesn't just suddenly disappear, but the intensity slowly changes. And by measuring the rate of change of intensity with respect to the apparent distance here, we can determine this derivative, the rate of change of density with respect to altitude, and hence beta. And knowing beta, we have everything we need to know to compute the deceleration. So let's take a look at a graph here, which is a plot of the maximum deceleration in Earth G's as a function of the lift-drag ratio of the vehicle. And we see that the decelerations for Mars are a lot less than for the Earth and Venus, and these in turn are a lot less than for Jupiter. We've indicated here also the approximate limits for human tolerance, and they're different for the different planets because of the different durations of the entry. Now, the point I want to make here is that if we compare a vehicle without lift, say L over d equals 0, with a vehicle with lift, we see that the maximum deceleration for the Earth changes from 8 Gs for a non-lifting vehicle to as little as 2 Gs or so for a vehicle which has a lift-drag ratio of only about 1/2 to 1. And this is a relatively small amount of lift. Now, besides using the lift-drag ratio to cut down on the decelerations, there's another reason for our interest in the lift-drag ratio. The L over d has an effect on the aerodynamic heating. Now, since the heating is the most intense at a stagnation point, we'll confine our considerations to that region. Let's suppose that we have here a body. Near the leading edge, the radius of curvature is r. As it descends through the atmosphere, a bow shock wave forms because the flow is hypersonic. And near the stagnation point, where the heat transfer is a maximum, the aerodynamic heating here convects into the surface a certain amount of heat, which we'll call dq dt, the convective heat flux. Now, at the same time, if the surface here consists of a thin sheet of metal, say, the temperature will increase to some value, let's call it Tw. And if we equate the heat that's radiated here away from the hot surface to the convective heating, we can determine and make a calculation of the maximum temperature that would occur during entry. Because the radiated heat is just proportional to the fourth power of the wall temperature. The proportionality constant involves the emissivity and the Stefan-Boltzmann constant. Now, the equation for the convective heat is a lot more complicated. It has a lot of variables in it, like the ones we've already seen up here, and I don't want to bother with them, but just indicate that the convective heating also depends upon a certain parameter here, the square root of the weight of the vehicle, the drag coefficient, and the area. So that in order to minimize the convective heating, we want as much drag as possible and as little weight. Now, a balloon, for example, would be a good vehicle in this regard because it has a lot of drag for its weight. And if a balloon came down into the atmosphere, it is so light that the deceleration would take place at a very high altitude where the convective heating is very low. Now, to complete this here, we have the radius r. So that this grouping here for W, let's say in pounds, the area in square feet and the radius in feet makes this pounds per cubic foot, which is in the nature of a density, and we'll call this the structural density. And for the moment, we'll set this equal to the unity and see what happens to the surface temperatures for vehicles as they enter into the atmospheres of the various planets. Now, on the second graph here, we have a plot of the maximum surface temperature in degrees Fahrenheit against the lift-drag ratio of the vehicle. And we can see right away that for all of the planets, the temperature is a minimum when the lift-drag ratio is only the order of 1/2 to 1. A very small amount of lift relative to what we're used to. We see also that for Mars, the minimum temperatures are less than about 1,000 degrees Fahrenheit. For the Earth and Venus, about 1,600 degrees Fahrenheit. And these temperatures are quite within the range which can be handled by existing structural materials. But Jupiter, the minimum temperature here is about 5,000 degrees Fahrenheit, and this is too high to be handled by at least existing structural material. Now, all of these computations here of the temperature, as I mentioned, are based upon a unit value of the structural density here. If we change that, we see that the temperature is going to change. So if we take the fourth root of both sides of this, we have then just the temperature. To take the fourth root, we'll have just the temperature. And on the other side, we'll have the structural density to the 1/8 power. So that as long as the structural density is not too much different than, say, 1 pound per cubic foot, a few pounds per cubic foot or something like that, the temperatures will not be greatly different than what we've seen. But this is not always convenient to design a vehicle with a structural density this low. Often we want to design one with, say, 200 pounds or so, or 300 pounds per cubic foot. So we have to look for a different technique there in solving the heat transfer problem. And here we can get a good clue from nature, because meteorites have a very high structural density, sometimes greater than 500 pounds per cubic foot. And if we observe them, we note that the surface of the meteorites has been consumed or ablated away, but the interior is largely unaffected. So we try to duplicate this process of ablation, and let's say instead of letting the temperature, in this case, rise to a very high value and radiate the heat away, we just put on a shield here, some sort of material, plastic or what, that can be consumed. And because of the intense heating, the material will be vaporized and the gas will form and pass on downstream here. And this creates a film here, a vapor, which adds to the effectiveness of the ablation process in managing the heat transfer problem, because there's a twofold action here. First, of course, just the fact that the material has been vaporized means that it soaks up a certain amount of heat. But then this other factor that I mentioned, that the film here in front exists, this blocks a certain portion, so that what we really have to handle is a smaller amount than before. Now this is a very complicated process here. There are a lot of chemical and physical processes going on that are very involved, and the ablation studies are currently receiving quite a bit of research, and we can expect that in the future that they'll receive a lot more. Now, thus far, we've been considering only entries which start from vehicles that are in a circular orbit. If we approach a planet from space, we have some different problems to consider. Let's say that we have a planet here, and we're going to approach it from a position out in space, about here. Now, the velocity is going to be different than the circular velocity. It's going to be more nearly the escape velocity, which is the square root of 2 times the circular velocity. So that somehow we have to reduce the velocity about 40% in order to get the vehicle into orbit. If we carried along a rocket motor, we could fire it in a reverse direction, but this would result in a very severe weight penalty. So we try to think of some way of using the atmosphere around the planet. Let's draw it like this, so that we pass through the atmosphere and use the drag of the atmosphere to slow the vehicle down to where it goes into orbit here. Now, clearly, we're going to run into a real guidance problem here, because if we come too close, we get into trouble, too close to the surface. But also, if we come too far out here, we get into trouble because the vehicle is not slowed down by the atmosphere, and it just keeps on going. Well, as it turns out, the vehicle has to pass through a certain strip of altitude here, which for the Earth is about 10 miles thick. So if we started, for example, from, say, the moon here, which is 250,000 miles, and wanted to pass through this 10-mile strip of altitude, it would require a guidance accuracy of 1 part in 25,000. Now, this is just about the same guidance accuracy that would have been required by William Tell if he had had to shoot the skin off that apple instead of just hitting the apple. It sounds like a very stringent requirement, but actually it's not, because suppose, for example, we went on a 2,500-mile nonstop airplane flight and managed to hit a runway 1/10 of a mile wide. Well, this is exactly the same guidance accuracy, 1 part in 25,000. And this is accomplished every day, of course, by aircraft, but they do have continuous navigation and continuous guidance. Now, as a final point, I'd like to mention that the aerodynamics of this type of entry here are in some respects similar and in some respects dissimilar to the characteristics we've already considered. The important points of similarity are, first, that with this type of entry also, the heat flux varies inversely as the drag coefficient, so that we want as much drag as possible. Secondly, for this type of entry also, the lift-drag ratio that is optimum for minimizing the surface temperatures for vehicles that are cooled by the radiation technique, like we discussed before, is also about 1/2 to 1, the same as before. So the point I want to emphasize is that we want as much drag as possible, and we want only a small amount of lift. Now these trends are completely opposite to the trends that have occurred in aeronautics over the last 50 years. We can see that from these models here. The Wright brothers airplane already had a lift-drag ratio of about 5. And this is 10 times the value that we're talking about now. After 50 years of development, always trying to get as little drag as possible and as much lift, subsonic airplanes like this one attain lift-drag ratios of about 20 and greater. Now we reverse this. We come to things like this, where we want as much drag as possible, so we have a very blunt vehicle. And as you can see, it's slightly asymmetric. It would have a lift-drag ratio of about 1/2, and this would be fine from the viewpoint of deceleration as well as aerodynamic heating. But it wouldn't fly very well, and it wouldn't land very well, of course, and have to be recovered by means of a parachute. So we try to think of a compromise between that and an airplane. So we think of something like this. In this case, we get a large amount of drag, not by bluntness, but by having the vehicle into the atmosphere at a very large angle of attack. And then after the peak heating is over, level off, and then go on. Well, a vehicle like this would presumably also have to have fairly blunt leading edges in order to take care of the heat transfer problem. As we can imagine, the aerodynamic problems of vehicles like this are very new to us. And likewise, we certainly expect that the major problems of propulsion, of getting a vehicle like this into space, which are also new to us, are going to be very difficult problems to handle. On top of this, when we recall and think that we not only have those problems, but also problems of guidance, navigation, which are very difficult. On top of this, aeromedical problems, which are orders of magnitude more complicated than we have before. These things all add up to a lot of very interesting and very challenging research for the near future.